All right, so at the end of our last segment, I kind of skimmed over this, but I have this little note about how there's a fact about music that the tube model can explain well. And in order to understand that, we need to understand a little bit about the acoustics of music in general. So, in some of you may already know this, some of this may be fairly obvious, but either way, we'll walk through it so we can get to the punchline at the end. But in Western music, there are these things called notes, which are what you play when you play the music, and each note is at a specific frequency. And the notes have different letter names in case you're not familiar with them. So like A, B, C, D, E, F, G, and then sort of the pattern repeats. And then there are a few notes in between, which are called flats and sharps. Not exactly an expert on this, but apparently in the German notation for music, there's also an H note. Who knows why? But for our purposes, we can just focus on these 7 notes. I should know that by heart too. Anyways, if you look at, say, a piano keyboard, the basic letter names for the notes are going to correspond to the white keys, and the in-between notes, the flats and the sharps, are going to be the black keys in between the white keys. And whether you're playing a sharp or a flat depends on what the overall key is, the pattern of notes that you're generally playing a piece of music in. We're not going to get into that. What I do want to talk about are the frequencies that correspond to these notes. So still remember, like, when I was first taught to learn how to play the piano, when I was a little kid, take the entire piano keyboard. There's 88 keys on an entire piano keyboard, and there's one in the middle, this white key here, which is called middle C. So you kind of learn that note as your reference point to begin with, and then you move on from there. Middle C, it turns out, has a frequency which is about 261.6 hertz. So you can kind of think of that. We talked about how an average F0 for an adult female speaker is usually around 220 hertz, so it's a little bit higher than that in frequency. There's also a kind of famous frequency, so the A above middle C, if you move on up the scale to this key here, this is tuned to 440 hertz, generally speaking, in Western music. And there's kind of a reason for that. The lowest note on a piano is the lowest A note, which is called A0, and that has a fundamental frequency of 27.5 hertz. So that's actually so low that it almost sounds like you can hear the individual pulses of the periodic pattern. Our ears can hear frequency down to about 20 hertz if they're in good working condition, so we're kind of at the limit of what normal ears can hear well as frequency, basically. And it turns out the way the piano or the musical scale is structured in Western music is that the frequencies of all the rest of the notes are multiples of that 27.5 hertz. It basically provides a mathematical foundation for everything else. So there's a formula here, which if you're kind of a math geek like me, you might find interesting, such that the frequency of the nth note, where n is the number of the note above A0, is going to be equal to 27.5 hertz, this baseline frequency, times 2 to the n over 12th power. So there are 87 notes above A sub 0 in all. If like you're 44 notes above the A0, then you put 44 in here for the N. I guess I can pick an easier number, like 48 for that N, and then 48 divided by 12 is 4, so 2 to the 4th power is 16, so then you've got 27.5 times 16. And I didn't plan for this, so I'll just do it in my head, but I believe that is 440, which is the A above middle C overall. So yeah, you can look at that here. This diagram gives you all the specific frequencies for all the various notes. The ones that are, the A notes give you this nice whole number like 27.5 to 55 to 110. Because there's a power of 2 here, every time you kind of repeat the cycle, there's 12 notes overall in what are called an octave. Then you get a doubling of the entire frequency. So 27.5 to 55 to 110 to 220 to 440, so on and so forth. And the ones in between do not look as pretty, generally speaking, but they go all the way up the scale to 4,186 at the very high end, this highest C here at the top of the keyboard. And I guess I'll just reiterate here. So there are like 7, white keys, and there are 5 different black keys. That gives you 12 total. So there's 12 tones there that you can play around with. And like I said, they're organized into octaves. There are 12 notes to each octave. And so when you go 12 note steps above a lower A, you get to the next A. And that frequency is going to be exactly twice that of the A that you just kind of left 1 octave lower down. So A1 is going to have a fundamental frequency of 55 hertz, whereas A0 had a fundamental frequency of 27.5 hertz. A2 will be 110. I think you see the pattern hopefully by now. As I mentioned before, C8 is about 4,186. C7, the next lowest C note, will be 2,093, and then 1,046, so on and so forth. I can't remember. I think wasn't middle C like 261, so that's about a quarter of this value right here. So 2 octaves below that. C4, which is also kind of a funny reference too, but I'll let you look that up on the internet. Anyways, so the central note is called middle C. It's about 261.6 hertz, and the A above that is 440 hertz. And most notes in Western music will generally fall within an octave or two of middle C, with some exceptions, which are kind of fun. So you can kind of think about this with respect to, like I said, the average fundamental frequency of most speakers of language, right? So for women, the average F0 tends to be about 220 hertz. For men, it's about 125 hertz. For children, it's usually around 300 hertz or so. So you can think about that, like for a male speaker to get up to middle C, which we think of as kind of like the default or average value for a note, perhaps, in the musical scale, you're already more than twice the average F0 for a male speaker. So that's relatively high, and most notes in Western music are kind of centered around that, generally speaking. So a lot of male singers, when they're singing, especially in popular music, tend to sing with a relatively high or falsetto voice when they're singing music. Like there's an exception of like Eddie Vedder for Pearl Jam, and every other guy sings pretty high in his range, right? For women, it's kind of around where their average F0 would be, but still a little bit above that. But you can go well beyond. Well, actually, that'll be the next slide. Here's a little slide about harmony, because we've talked about harmonics in terms of complex sound waves. Harmony is also a term in music for similar reasons, not quite exactly the same thing, but notes are said to harmonize with each other if the greatest common denominator of their frequencies is relatively high. So here's what a A4 sounds like, the 440 hertz note. That nice, beautiful tone in sine wave form. So that's going to harmonize well with, in order, the next A above it in the scale. Yeah, I don't know if that sounds so great. But there's a high greatest common denominator for those two, so you can kind of intuit that there's a fundamental there that both notes share. You can kind of think of these two tones as like two harmonics of the same complex wave, because you go from 0 to 440 and then 440 to 880, which is what you'd expect for harmonics of a complex wave with that fundamental frequency. E5 is the note sort of in between those two A notes. It's not exactly 660 hertz. Actually, I don't remember what it is. It should be in the scale somewhere. E5 is 659.25, so it's not quite exactly there, but it's about 660. So when we play these two together, they're going to kind of sound like they have a fundamental frequency of 220 hertz. That's the greatest common denominator of those two frequencies. So that sounds pretty decent. This is called a fifth. If you've ever encountered it in musical form, you probably are already aware of that. So it's like 1, 2, 3, 4, 5. It's the fifth white note you get up from the A. C sharp 5 is about 550 hertz, so this will sound relatively well or good with A4 as well, because you get more or less a greatest common denominator of about 110 hertz for those. So they sound like they're two harmonics of a note with a fundamental frequency of 110. As you get closer and closer, though, to that A in the musical scale, though that greatest common denominator is going to get smaller and smaller and kind of harder to perceive. So you can play an A with an A sharp. This is known as a minor second. This one is, by the way, a third note up in the scale. This one is not really going to sound that great because it's hard for your mind to kind of intuit a fundamental frequency of 2 hertz which is the greatest common denominator of 466 and 440. Yeah. And you get kind of that beating effect there too, perceptually, where they're kind of interfering and, going in and out of phase with each other, as it were. So that doesn't sound good. You can also get a major chord, which is this guy, and this guy all together. They should all sound like they have a greatest common denominator frequency of 110 hertz and actually sound pretty good. More or less, that's a nice happy little triad of tones. That's a major chord. So basically that's why things harmonize, because the notes sound like they're harmonics of the same complex wave. You can think of it in those terms. Like I said, we can go well beyond this range, though, that we've been talking about to this point. So not all music stays within a couple of octaves of middle C. So I've got this example. Actually, I didn't test this before I started, so hopefully this works. This will work. It's from a piece by Mozart. It's not found. I'm going to have to play it in Prot, and hopefully you didn't see that. So yeah, here we go. All right, so fun times. She probably sings higher than you do, but maybe not. I've actually had a few students in class who at least claimed they could sing this high. I cannot. The piece of music that she's singing is called Der Hölle Rache kocht in meinem Herzen from Die Zauberflöte by Mozart. This means the magic flute. This means, I think, Revenge of Hell cooks in my heart. Which does not seem to line up with the happiness or the happy sound of the music. So take that, Nirvana. Mozart figured out how to do that 200 years before you guys did anything. This is sung by an artist named Sumi Jo, and I'm also going to mention here that I got this example from a former professor at Ohio State named Mike Bro, who basically produced a lot of the materials in this class that I've presented to you. So a lot of the credit for all this fun stuff goes to him. Yeah, so the fun part of this is that there's a F6 note in this particular piece of music. And the frequency of F6 is 1,397 hertz. I think I've got that here. Yeah, it's that note. Most sopranos cannot sing that high. We can look at this, though, again. We can go through this excerpt, and I think you can hear it. I think it's somewhere around here. Yeah, so this is what the spectrogram looks like, and we're going to change the pitch settings to be unlike we've ever seen them before. We'll put 1500 at the top end. I think we'll get there, right? Maybe it's not getting it. It's too high. Yeah, so no, it's not getting it. Anyways, we can listen. There we go. Yeah, still doesn't want to grab the pitch for that particular note. Like I said, I have had some students in class who said they were trained classical singers and that they were able to get up that high. And then I've also had some who said that they used to be able to get up that high, but when they get out of training, they can't always do it. So with some practice, you can expand your range, evidently, basically figuring out how to coordinate all the relevant muscles together, and then it gets easier or maybe harder if you stop practicing. Yeah, but it also depends a bit on the equipment you have. So I definitely, no matter how much I practice, could get up that high. I think we saw before my highest end of my F0 range is like 750 or something like that. It helps if you have shorter tensor vocal folds, obviously, and it helps, therefore, if you're female and are more likely to have equipment that is of those specifications. So the interesting part of this is that are there any potential problems? I don't know why I did that. Are there any potential problems with singing this high? I've asked this question in class a lot, and people usually pick on some other problems that I'm not thinking about, so I'm just going to walk you through the answer. But usually people think about what's the problem with like physically doing it. Is there any damage you could do to your articulators or whatnot? And that's not really what I'm looking at here. Instead, the issue is an acoustic one, which is kind of funny to think about. So the F1 of most vowels is generally going to be below 1,000 hertz. It doesn't matter what vowel you're playing around with. So we just saw in the beginning of this lecture an example of ah, which is kind of a classic low vowel. In the idealized case, it would have a F1 of like 920 hertz. And that's the highest value of F1 you could reasonably expect from sort of an adult male speaker, right? But F1 is normally going to be lower than that, especially for mid or high vowels. And even for females who have shorter vocal tracts than males, generally speaking, they will have higher formant frequencies, but normally their F1 is going to be below 1,000 hertz. So what that means, or the problem here exactly, is that when you are singing a note like F6, which is about 1,400 hertz, and F0, there are no harmonics below 1,000 hertz for the vocal tract filter to amplify. So if you remember what our power spectra looked like, we had like a series of harmonics going up the scale, and then some of them would be intensified by the resonant frequencies of the vocal tract, and some of them would be damped out a little bit. And the harmonics that fit into the resonant frequencies, the characteristic resonant frequencies of the vocal tract, would form the formants because they would become more intense, and you could kind of hear them a little bit better. They'd stand out, as it were, in that sort of classical pattern that we get for vowel formants. But there's a problem here because we don't have a sound source. It's like you don't have a harmonic for the frequencies that the vocal tract wants to resonate at. So I mean, going back to like my Coke bottle example, like I told you that when I blow over the top of the tube, I'm sort of stimulating all frequencies across the board. And so there's a few that will match up to the resonant frequencies of the Coke bottle, and they'll become more intense. But it's sort of like, in this case, I'm applying basically like a high-pass filter to my source and saying I'm not going to have anything at the lowest frequencies. I'm just going to start at like 1,400 hertz and move on. So if the resonant frequency of this tube, this bottle, is like, I don't know, 400 hertz, and I'm only producing source frequencies above that from 1,400 on, it's not going to resonate at all in the way that I'm normally thinking of it resonating. Same thing here in this particular weird case where we have a vocalist who's singing a super high note. She's going to produce the source sound for whatever she's singing, but she's not going to be able to get that characteristic resonance that we're used to listening to when we hear her speak. So on the surface, it seems like it would be impossible for singers to make like an F1 based vowel distinction when they sing that high, but they have a trick up their sleeve, which is famously known as the singer's formant. So this was discovered 50 years ago now by another Swedish phonetician named Johan Sundberg. And he looked at what vocalists do when they actually do sing, and he found out that they have a really high formant that most people don't produce when they just speak. So this is a graph which was derived from his original paper on the topic. So there is a dotted line here, which is kind of like the average spectrum for everything a person says. And it gives you sort of more energy here down at the lower end, sort of centered around 500 hertz. And then, as we know, the harmonics kind of tend to drop off in intensity as you go up the frequency scale when we look at the source properties of speech, right? And it kind of applies across the board to all the different filters we apply to it when we speak different sounds. Interestingly enough, the sort of spectral curve of an orchestra, a classical orchestra that might be playing along with a vocalist in, one of Mozart's operas or what have you, it almost follows the exact same curve as what we see for speech, in that it has this kind of peak in intensity at the low end, and then it just kind of drops off from there. What singers do when they sing, though, on average, they produce a spectral curve that looks like this. And there's a little bit of a bump here around 1,200 or something. But then there's a bigger bump here, more in the 2,000, 3,000 hertz range. And that's interesting. What Johan Sundberg hypothesized is that this makes an opera singer stand out more in contrast to the orchestra over which they're having to sing when they sing in an opera. If you can think about that, in the olden days when opera emerged into an art form, like in the 1800s, uh, there was no artificial amplification of anything, right? So you were just in a concert hall and there was an orchestra playing and then you were singing and you had to have the vocal power to project yourself over the orchestra. I've got the din of the orchestra here. We can say the beautiful music perhaps of the orchestra, but either way it's pretty loud, or it can be pretty loud. And if you're just a soloist, you have to figure out a way to sing louder than that so people can kind of zoom in on you because you're the most important character in the whole shebang. And so the idea was that this kind of makes that vocal sound stand out a bit in contrast to the orchestra, even without a microphone for the vocalist to sing into or what have you. And so this became, I guess, part of musical tradition, and it continues on to this day that singers are trained to sing with this singer's formant. It also provides them, or potentially would provide them, with higher frequency resonances for higher pitched notes like this F6. So I've got, hopefully this will work, but I've got just the, I don't need Bruce anymore, the F6 note here. Is this turned on? Oh, maybe that was a problem. Yeah, got it. Never mind. So does this work now? Yeah, there we go. Yeah, so you can kind of see the beautiful jumps here. That also takes practice, as you know, if you really want to sing well, to be able to get your vocal folds to make those dramatic changes. I think in part this is also influenced by the sound of the orchestra in the background, but let's zoom in on this guy. Yep, like I said, this F0 is around 1400 hertz, where it ought to be. If we just check out the spectrum of this note, holy smokes, look at that. So, yeah, let's zoom in on a little piece of this. Might make it easier to see. Yeah, so I don't know if that helped at all. Why bother practicing ahead of time when you can just improvise on tape? Okay, yeah, so that's the F6. This should be about 1400 hertz. Our next harmonic should be at 2800 or so, and this should be 4200 or so on. Yeah, so it's not super easy to see formants here. When we look at this, we can kind of see just a lot of intensity here, a little bit less intensity here, a little bit less intensity here. These are basically the harmonics in the source signal, but they look kind of like formants because there's not much else going on there. I can tweak the spectrogram a little bit. We can look at the narrow band. It might be easier to see. Yeah, so these are our harmonics just at that particular spot. And this stuff in the background, the fainter lines, are the harmonics for the orchestra, right? You can kind of hear those strings a little bit in the background. The idea is the singer's formant should be able to boost this harmonic a little bit. And it's not exactly an E pattern. We have a nice low F1 and a higher F2, but you're getting some separation between these two. So this harmonic can kind of function as the F1 for the vowel, or this harmonic can function as like F2, that sort of thing. She's kind of singing more of an ah, I guess. Let's go back to Prot. But in theory, she could use that singer's formant as kind of another formant, a back pocket formant, as it were, in case she needs it. Let's just do this part. Yeah, so that's kind of the joke that I heard somewhere along the way. She's singing like an ah. Supposedly in the olden days, back in the preamplification days, composers were taught, if they went to composer school or whatever, that there is this problem with just the acoustic structure of speech, that it's difficult to produce high vowels when you can't sort of rely on low fundamental frequencies to give you that sort of low F1 that you need to produce for high vowels. So they were taught, supposedly, that you should not require a singer to sing a high vowel on a high note. And it kind of works out as well with regards to the amplification issue, because if you open up your mouth more for like an ah, you're getting more intensity out than for like an e. And you kind of hear singers do this in popular music as well. Like e's often come like ah, a, something like that. So yeah, Mozart was a good guy, and he composed this music so that she's singing an ah for these notes. Supposedly Beethoven was taught the same thing, and he's like, I don't care, they can just deal with it. So singers use sing an E with a super high note and just figure out how to do it, even though it's impossible, because that's the way Beethoven was. And we'll just move on and enjoy the music. Anyways, how do they do it? So the idea is that classically trained singers, or just anybody who figures out how to do this, can form a short, narrow tube near the glottis by making a constriction with the epiglottis. So if this is the vocal folds and we're moving air in this direction from left to right, this is your epiglottis, and you can kind of constrict it so that it makes a constriction of about an inch in length. And if you walk through the math of that, so you can kind of think of that if an overall vocal tract length of like 18 centimeters has in F1 of 500 hertz, and you shorten that by a sixth, so divide 18 by 6, you get 3 centimeters, then your first formant frequency should go up by 6 times, so 500 times 6 is 3000 hertz. And that's how you can get that high singer's formant. Isn't that cool? And I can give you a video. We watched this a while back, a long time ago. If I can find it. Yeah. This guy. So he's forming a tube with his epiglottis, and I don't know how he does that, but here's his vocal tracts. This should be a tube about an inch long, and let's hear what it sounds like.
And him that plants him is soon forgotten.
Yeah, so it's kind of got that classical feel to it. I haven't double checked to make sure it has that singer's formant in it, but you can tell that guy knows what he's doing, especially something, whatever the heck he's doing with his epiglottis to make that work. That's how you get that acoustic effect. I will end this bit with one last note about music, which is to also go back to a form of music we listened to before, which is this overtone singing. So if you remember, for this form of singing, we have F0 staying at the same level throughout, and then the singer can kind of change the shape of their vocal tract so that individual harmonics will resonate more or less. And by this point, I think we kind of know what to predict here looking at the spectrogram, and we've heard this before too. This is a narrow band spectrogram, so you can see the harmonics quite well. This is kind of a consistent low F1 as we go through here. We have a kind of lowish, what looks like an F2 at the beginning of this. So low F1, low F2, that should sound like an E, or ooh, sorry, something like a high back vowel. And then kind of go through the scale here until we get to something that sounds more like an E at the high end here. So I'll play that, and as I play it, I'll kind of present the question I want to ask. Yeah, so kind of goes from ooh or oh to E, and there's kind of like an here in the middle, where maybe F2 and F3 would come together. Either way, though, what kind of voice quality would you want to use to do this? This is also a question I've asked in class many times, and not often gotten a very quick answer, at least, well, neither a quick answer nor a correct answer very quickly. So I usually let everybody think about it for some time. This is the end of the lecture, though, so I'm not going to sit here for 5 minutes with nothing else to follow up on while you try to figure it out. Maybe you figured it out already, though, because we already kind of know what voice quality is used for overtone or throat singing, which is a more tense voice quality, right? So the reason behind that is that if you have a tense voice quality, you have less spectral tilt, right? It's a square waveform coming out of the vocal folds, so you have more intensity of harmonics already to begin with at the higher end of the scale. So if you wanted to be able to have the liberty of, picking particular harmonics to emphasize as you sing, would be easier to do so if they have more intensity to start off with. And that's kind of basically why you'd want to learn how to sing in a tense voice if you're learning how to throat sing. It gives you kind of more options which are easier to hear for harmonics to pick out in the scale to give you that kind of eerie two-tone effect where you get sort of the monotone F0 and then a really prominent harmonic above that. Cool. So that's all I'm going to say about music for now. We'll talk about sonar and acoustics next time, and then we'll lead in from that to our first discussions of how we actually perceive speech. So I'll be looking forward to that, and I'll be looking forward to seeing y'all again. All right. Bye.